So I'd like to talk today about what's required to do messaging and real-time systems for Hadoop-ish computation, using Hadoop-ish in kind of the very large sense of the entire ecosystem. That includes things like Spark streaming, Flink, and so on, that are not, strictly speaking, Hadoop themselves. So I'm going to talk about those requirements and what the particular implications of the requirements are. And I'm also going to talk specifically about how MapR, this is a sponsored talk here, I don't have to be quite as vendor neutral as usual, how MapR is responding technologically, giving some of the internals of what we're doing in order to support these new kinds of applications, new kinds of open source projects. My name is Ted Dunning. I'm Chief Application Architect for MapR. Red guys. And I'm also a committer and PMC on, I have to say, a lot of projects anymore. I can only count to 2. I'm a binary kind of guy, and so it's more than 2. I'm also the VP of Incubator at Apache, which means that I get to help moderate how projects come to Apache. Some projects are appropriate for Apache. Some have needs that Apache can't meet or want to do things that Apache doesn't do. And so the incubation is the process by which we bring new projects into Apache. And that's an exciting process. It's a tricky process because a lot of people have focused on development, not on releasing in an open source way. And so the incubator is how we mold projects into the Apache way. You can contact me by email, private email, Apache email, public email, company email, or Twitter, or catch me in the hall, catch me at the booth. You can catch me pretty much any way you like. A lot of what I'm talking about today is contained in our book. Ellen's in the audience there. I've written a number of 6 books now on different topics. This latest one talks about the implications for architecture of recent technological developments in streaming, how that changes what you want to do. And that's going to be the first half of this talk today. You can get a copy of the book today at 3:40 at the MapR booth. We'll be signing it, getting writer's cramp and so on, but also having some good talks. And so the goals of what we're trying to do in the context of today are real-time or near-time computation. That includes honest-to-God real-time, which are computations with deadlines, but it also includes situations where delay is just not good, not forbidden, just frowned upon. Now, it's my contention that the world works this way. Other people may have other experiences. They may have delayed their entire childhood to be consumed at a batch when they reached 18. Some people may work that way, but I think mostly the real world doesn't, and that the batch computation is an artifact of banks. Essentially, at one time, they had bankers' hours. They had some time in the morning to get ready, then they did the day of business, they collected all those results, and in the evening, they would apply those results. They were the original batch-oriented business. And they were the early drivers of computation. But that's not so anymore. Banks don't even really close anymore. They stay open effectively for all kinds of transformations on accounts and moving money and such, 24 hours a day. The banking day and bankers' hours and posting time are fictions in the modern world. They're not reality. And so as data becomes more and more available in a streaming mode, the demand for computation to proceed in the same style is substantial. It also gives us big simplifications. And the simplifications come from the idea of using microservices as an idiom for architecture. We can build systems in a very, very simple style that way. And that can give us some really powerful capabilities. Partly we can use the time we have to have a life, or we can also use the time in order to build bigger and better systems that handle more complex situations if we don't have to worry about the muck of simple logistics. So the point here is flow versus state. writing computation in a flowing style. And one of the consequences is that real-time and near-time become fairly easy. If you look at batch or even microbatch, when you do batching, you have elaborate workflow requirements, timing, and a dance that you have to do. You've got a little bit of data, you do some processing, then you merge it in later, and if something is late or something is broken for a moment, then later you have to catch up, and you have these scheduling constraints, and you have things, big loads on the system right on the hour, and so on. It becomes really complicated. But if the data is naturally a flow, it becomes much easier. These artificial boundaries of every 5 minutes, every hour, every day are relaxed. In fact, it's really much easier in many ways to write these programs and to run these programs. If you think about it, if we're running in real time, which sounds really hard and scary, if you're running in real time over the last 3 years, you had 3 years to process your data. If you do it in batch, you typically have 5 minutes or an hour or something to process the last 3 years' data. It's easier to do in 3 years than it is to do all at once at the end. So life doesn't happen in batches. This is a really natural way to compute. So I'm going to give some background. We're going to talk about global requirements, and then I'm going to talk about how we build technology that scales. So the first is a terminological thing. A microservice is a service, I didn't write that part down, which is loosely coupled to other services, meaning if you mess one up, it doesn't mess all the others up. And it has bounded context of change. If you change one and improve it somehow, in many cases, none of the partners in computation have to change right away. They can change to make use of this new capability you've done, but they don't have to. That means that when you make a change in one place, that's all that has to change right now. That's all that has to work correctly right now in terms of the change. And now you can propagate to a neighboring service to make use of that change and propagate slowly. So you have very, very bounded context of change. And that's really important when you're trying to actually build systems that run. Now, one way, and these are the traditional ways of coupling services together, sharing schemas, sharing relational databases, ad hoc communication technologies, enterprise service buses, all of this, I think, are things you should not do, even though they are very strong traditions. Instead, I think what we should do is we should use self-describing data. We should use private databases. Databases are still critical. But to the extent feasible, they should be relatively local to individual services. There should be infrastructural communication. By infrastructural, I mean it's kind of like the air. Most of the application developers shouldn't even think about it. A good measure of that is 50 or so years ago, if you were going to build an application and you wanted to have a file, you would have to go ask permission to have a file. You would have to negotiate with a system administrator about whether or not you could have a file, how big it could be, and where on the disk it would reside, and what would we do if it got bigger. And if you wanted 2 files, you'd have to go back again. You'd have to go to a committee practically to get a file. Now, this is dark ages, and most people in the room don't remember those times, but it was nuts. I mean, it made sense in the time because computing was, we did it with rocks because they hadn't invented dirt yet. It was a long time ago. And it was a sad time to have to do these things. But we are still in that situation. If you want streaming infrastructure, you have to go negotiate with an administrator to get a cluster set up for you. If you want tables, you have to go negotiate to get tables set up for you because multi-tenancy doesn't work there very well. Well, my feeling is that this stuff should be like the air, just easy. As hard as it is to make a file, like touch, XYZ, that's how hard it is to make a file. To make a streaming infrastructure, you should be able to build a stream with one command the same way. Maybe a second command to set the permissions, or something like that. That's how easy it should be to do streaming. That's how easy it should be to have tables. They should be multi-tenant and as scalable as we have files today. So that's one thing to do, is make it infrastructural. Use modern protocols that are future-proofable and adopt those practices that make it so. And then use shared storage. And by shared, I mean multiple people access it, not that it lives in the same infrastructural cluster, where necessary due to scale. So what's the right structure then? Traditional message queues are not. Kafkaesque. Kafkaesque in the sense of a persistent, performant, ordered log, I think, is the right answer here. Logs are like queues. They give ordering. They give multiple consumption. Out-of-order consumption is possible where we need it for scaling and speed. The canonical implementation is Kafka, and the Kafka API, I think, is the way we ought to go. Performance and persistence. So let's look at this. Suppose we have a little black box. It's white here, but that's an implementation detail. So it's going to be making decisions. You ask it, is this thing a fraud? You ask it, is that thing a fraud? And it gives a decision back as quickly as possible. Now, we could make this be a microservice, and this is traditional kind of microservice, a query response kind of thing. You query it, and it gives you a response. How do we implement it? One way is that we give it a database, and so it remembers where you used your card last, how much you spent, and so on. Now, if we want to scale this, this is the traditional way to do it, is you share that database across multiple little fraud detectors. And that leads to this situation. Now, this is a scalability limit that is not a technological problem. Now, there's technology too. I mean, I talked to a big payment services company a while back, and they were saying, we do 65,000 transactions per second. We spent $100 million to do that. I'm going, wait a minute, I'm a little confused here. I could do that on my phone. So this is not really a technological limit unless you build it in perverse ways. It is a human limit, because if you share a database, if you share a schema like that, you will share committee meetings with all of the consumers of that database, and things will grind to a halt because you have to agree on every change. Brittle schemas and schema evolution in this kind of environment is an abusive, invasive kind of thing. And so this is not the right way to do it. A much better way to build such a system is to build the box and put the database in the box and don't share it. What we do is we pull out of the box a stream of business level events. Now this is kind of weird because it breaks the idea that we might have transactional updates to that database. I mean, they're transactional in the sense of atomicity, but isolation and so on goes away. Not such a big deal if we're not sharing that, because we can now order it, we can make those business events that go out contain all the information that's necessary. By exposing this stream outside here, which has high-level events, we liberate the service to change how it represents that. And more importantly, so you can imagine, for instance, the CEO says, I want a dashboard in the lobby that shows where transactions are happening in real time. Now, if you're using this style, everybody goes, oh God, we have another consumer for the database, it's going to break everything. And they say, no, we can't do that. But with this style, all you do is you add a few more consumers to that stream, and you don't affect this real-time service at all. You can put your little dashboard up there very, very easily. You can put your data mining activity where you're recording an archive of long-term data very easily. You could also scale the service just by replicating it, and this one could be using an in-memory database. This could be using a database on flash. One could be using a completely schemaless database. The other could be using strict schemas. It doesn't matter. This guy can't see that database and vice versa. They're completely isolated except for the fact they see the same business updates coming into their database. So they are roughly synchronized. Roughly is good enough. In fact, roughly is better for concurrent processing. So this is the microservice, the streaming microservice kind of style. You can see how it's changing things, but you can also see how some things can be made much easier. Suppose we're the biggest credit card company in the world. We've got 100 or 200 million accounts, and you want to keep a fraud history there. Well, that's like a kilobyte per account. So this database might be somewhere between 10 to 200 gigabytes of RAM. That's really easy. That's not a big deal anymore. Used to be a big deal. So maybe we want to evolve to that. If we had to share it, if we had to share that database between different applications, we couldn't specialize it and make it as small and efficient as that. And so this is an example of how it's much easier to build these systems in this style. Decoupling and isolation are key to this, and private data stores are very, very important, but global storage of private data is a bug. We need to propagate business level events, not table updates. Okay, so here's some scenarios for that. One is data aggregation. This is the shape of the business. Say a drilling company, they have multiple locations, drills. Sometimes you move equipment from place to place, but mostly there's big assemblies, and they want to aggregate that data into a central facility. Now, each one of these pumps in there has many measurements that you might make on it, temperatures, pressures, flows, and things like that. And so at each one of these drilling locations, you have lots and lots of pumps. If you can do good streaming, you can make this system look very, very much like the business. And if the system is shaped the way the business is shaped, then it becomes very natural for anybody who's involved in the business to understand the data system. The world gets much, much simpler. And I contend that you actually need first-class replication between these different facilities in order to make that really true. So data architecture should reflect business architecture. Even very, very simple designs often require multiple locations, at least if that's infrastructural and free. And you have to have, of course, real-world constraints like schemas cannot be frozen, and you need to match your security to your business structures and data ownership. Here's another scenario. This provides the example of how flowing data on a global scale really makes a big difference. Suppose we have a ship, we have a port, we have a corporate galactic headquarters there, and we've got containers. There's about 20 million containers in the world. 6 million are active at any given time. And anybody who has stuff that's in a container wants to ask the question, where is my container? Where has it been? What ship is it on, or what dock is it sitting on? Where is it? What's happened to it? How is the temperature, whatever happened to it lately? And so it's really natural to have one topic in a flow per container, because that lets people just subscribe to one topic and they get the information they want as soon as it's available. So these would be 5 topics for these 5 containers, and they would be reporting into the Tokyo database. Well, the Tokyo stream, not a database anymore, because we don't do that. And that would replicate to galactic headquarters and maybe out to partners selectively. Now we put the containers on the ship, and now they report into the data center on the ship. The data center is probably not much bigger than my phone. You know, it could be a couple of NUCs. It doesn't have to be a big data center, but it's still a data center in that it's got a cluster, and that would continue reporting into the port database, replicating data. Now, since the containers only reported one place at a time, the replication patterns are really simple. We do this, for instance, in our implementation of streaming. Now, the ship's going to go to Singapore. It's going to be out to sea for a while, so it's going to be reporting without replication for a period of time, maybe a couple weeks. Well, it shouldn't take weeks to get from Tokyo to Singapore. And then when it lands at Singapore, it's going to replicate all that data, which is going to replicate all around. And as long as the topics, the containers, only report at one port at a time, one harbor at a time, it should be just fine. Now, you have scalability issues there against things like Kafka, because Kafka doesn't like more than about 1,000 topics in a single broker cluster. But if you break that limit and go like we do with MapR Streams, you could have hundreds of millions of topics quite reasonably. And you can see how matching the data architecture to the business is containers go on ships, ships move from place to place. If the data architecture matches that, data comes from containers to the ship and occasionally to the port. It's really suddenly simple. We have one data structure, a big stream with 10, 20 million topics in it, and you could get the answers you need in real time. So the lessons to this are updates must be multi-master. You need to be able to update a single topic in different places at different times. You have to have an arbitrary number of topics in order to make this simple architecture simple. Mobility implies change. So I'd like to talk a little bit about the converged requirements. So we see long persistence and hundreds of millions of transactions per second. We see that a need for files, tables, and streams. We need volume, snapshots, mirrors, permissions, of course. I mean, this is enterprise sort of things. We have to have platform security. Cannot depend on perimeter security ever. You can implement it, but you can't depend on it. And you have to follow the business structure at business scale and scope. Well, we think, therefore, the right thing to do is perhaps to develop new technologies in there and match open APIs. The commonality and interoperability is absolutely critical. If you compare Hadoop to the NoSQL world, sadly, the NoSQL market size is effectively 0 when you compare it to Hadoop's market size and do round off to 2 significant figures. The reason for that is because of the balkanization of the NoSQL world versus the interoperability of the Hadoop world. So we have to have common APIs. We have to have these levels of performance. And so in streaming right now, what that means is the Kafka API. The Kafka 0.9, the 0.10 APIs are very, very good for this kind of thing. The only problem is some of the implementations are weak. So here's how MapR has responded to these needs. So over time, we started in the dark ages. I described that. That's where you had to go ask permission to have a file. And Linux and POSIX and modern systems improved the functionality and compatibility of systems dramatically. It used to be that you couldn't read a file on different systems with the same code. Mind-boggling that that was true, but it was. Now, Hadoop came in and gave up essentially all of that functionality and commonality in order to get scale. That's what HDFS did. They gave up mutability. They gave up access via normal APIs. They gave up a lot of things, but they did get a lot of scale. And our original business thesis was that we would up the scale and give back a lot of that commonality. But we think that beyond that, you need to go further and add new data structures, new technologies. Beyond that, you can see the change in the logo color represents the passage of time. This is how you mark time in a corporation, is you change the color of your logo. And so the point that we are now is that we have performant systems. Samsung says that we're the fastest big data on Samsung Flash. And we're talking about saturating, that's gigabytes per second, by the way, saturating multiple 100 gigabit network links. This is per node, not per cluster. And so we can put this superb performance together. And the way we do that is we build using C++ at an integrated level, maintaining these common APIs, maintaining POSIX APIs, maintaining HDFS, the HBase API, and now streams. And the way that this works is we started by adding volumes. We heard a talk previously about federation. This is multiple clusters in order to get scale. But that massively increases the administrative overhead and the complexity of programming. We think volumes as an administrative concept are critical, but they cannot require separate administration, and they cannot require isolation of hardware. We also added read-write random access file system, access via NFS and by high-performance views, high-performance network bonding, and transactionally correct snapshots and mirrors. The way we did this is we chopped files up, put them into a new thing called a container. These were called chunks, containers, and then those are replicated across the platform. We put transactions in the container level, not the file level. This is essentially allowing us to multiply 3 numbers to get scale. In HDFS, you have number of blocks times the block size. Number of blocks that a name node can handle times the block size is what you get for scale. Here we have number of containers times container size times block size. So we multiply 3 numbers, get higher scale. This is the secret sauce where the transactions work at that level. And then containers and processes mostly talk to each other. The container location database is a reference, not a core component. As I mentioned, we multiply to get scale and easily to 2 exabyte level. We currently have multiple customers at multiple tens of petabytes, total management easily in the multiple exabyte range. I'm going to leave that in for reference. I'm not going to go into the details. But one of the cool things is the core data structure inside a MapR system is a B tree. This B tree is implemented for files and directories. That's wonderful. But tables are also implemented that same way. If you take tables, a big table like this in a MapR system, it's just like a file. It looks just like a file, except it's not. You can't do file things to it. You can only do table things to it. That's split into what are called tablets. In HBase, those would be called regions. But these are very different because these are split again at a second level in MapRDB so that you get partitions, and then partitions actually have substructure as well. And then very unusually, relative to things like LevelDB or HBase, the lowest level data structures are mutable. They are internal B trees. So we get some of the benefits of an LSM in terms of simplicity and parallelism, but we get very, very high performance, low and bounded write amplification. We don't have to do the compactions that normally attend with a log-structured merge tree. That allows us to take the partitions of a database and spread them into containers just like we took pieces of files. Now, I could repeat the entire story again. That's how we implement streams as well. Multiple messages under keys in B trees, tablets being split across like that. But we put a standard streaming API on it instead of a table API. Performance is very high. The highest performance, for instance, for Apache Flink ever was recorded on a MapR cluster. So here's an example of what I mean by convergence. This is my home directory. I'm on a cluster called SE node. Well, SE node 10 is the node that I'm on. The cluster name is SE1, and I just do an ls. This is legacy code, obviously, ls. And you can see files, streams, and tables in my home directory, also directories. If we magnify this lower part here, you can see the cluster. So I have access to all the clusters in the world that I am allowed to. And I can have my home directory on any one of those. Any program can access any data. You don't need federation for this to happen if you have a good technology underpinning. So the lessons for all of this, APIs matter far more than implementation, at least in terms of commonality, in terms of community. There's plenty of room to innovate way ahead of the open source community. Now, I've been in open source for a long time. This is not a dig at open source. Open source communities do evolution, not revolution. They work with progress, not perfection. So building that community is the key thing for the open source to do. That involves consensus about APIs, and that lets us get together to build things. But there's room for alternative implementations which bring new and exciting capabilities. So, call to action to everybody here, support common APIs, absolutely. And do come by and visit us at the MapR booth. We'll be, we offer free Hadoop training, not just in the booth, but online. We'll be signing this book today. And we have 6 ebooks total that are available from the MapR site. So you can get them in either PDF form or some of them, the most recent ones, you can just read directly online without a download. Thanks for coming today, and we have just a little bit of time to ask questions. Of course, the real place to ask questions is the MapR Converged community, but I'm happy to take some questions right now. Anybody got, yeah, Slim.
Yeah, this is a rather comment, not a question. I wish you had touched a little bit on another two big advantage of the architecture that you showed. One, the ultra low latency, because here you are killing couple hubs. You don't need a dedicated Kafka cluster, because this is one cluster. You don't need another cluster when it comes to showing the data. You don't need, for example, Elastic Search cluster. So that's number one, the ultra low latency. And the second one, when it comes to hardware. So here, definitely, there is like operational efficiency in the way you show this architecture. And I would like to say, this is just an opinion. I'm not paid by MapR or by anybody to give my opinion. And I'm free man.
So Slim's making a good point. I didn't emphasize latency, but of course, since we only have a few minutes left even now, I didn't have much time. And also the efficiency of hardware implementation. He does not work for MapR, but this is just what our customers and partners sound like. Sorry about that. But he's a good guy. Any other questions? I'm happy to answer questions specifically. Yeah.
You mentioned the architecture should mirror the structure of the business.
The data architecture should match the structure of the business. The infrastructure architecture should be divorced from the business structure.
Yeah, and I think you were saying that because of that, you may want to have multiple data centers in different locations.
So yeah, I did say that you would want multiple data centers. And it's very natural if business goes on in multiple places. You need the ability for business to proceed even if they become isolated.
Yeah. Can you give other examples how the data structure should mirror the business structure?
Sure, I can give plenty of other examples. One is with a bank. Some data must stay in a country, some data must not. So the fact that some data must stay in a country means you have to have a data center in every country that you do business. The fact that it must not means, I mean, for instance, money laundering and fraud information, you require that it be moved out of the country very quickly so people inside the country can't cover up malfeasance. These are regulatory requirements on banks. And so that defines already some of the business structure that the data should follow. You should be able to have data in place and access it from other places. You should have automatic replication that is inviolate, that moves that data, the critical data, out of that to a safe location. So both of those are data architecture that has to follow business architecture. The ships were another example. The field operations for pumps. The pumps are just like a cell phone system, except they pump stuff out of the ground, whereas the cell phones pump waves. But the requirements are very much the same in terms of data architecture. You have stores. Every store should have data acquisition, should function independently. It should move the data to the central site automatically and magically without application intervention. And it should do it securely, safely, and encrypted. All of these look the same after a little bit, at least from the infrastructure level looking up. But yeah, you just see it over and over again. Businesses don't all happen in one place. Any other questions? We have room for, I think, one, maybe two more questions, depending on whether or not I can shorten myself. Yeah?
So how does this, there are other streaming technologies, the Storm and so on. How does this compare with it?
So he's asking about other streaming technologies like Storm and so on, and Flink and Spark Streaming and Samza. Well, what I've talked today about is the transport technology, which is really the infrastructural piece. There are two parts, like two hands, that go together. One is the transport. You have to move the data. The other is the processing. Flink, Spark Streaming, and Apex. All of those are processing. Kafka, Apache MQ, RabbitMQ, IBM message queues, and MapR Streams are all transport. Now, I think for the modern type of big streaming applications that we're talking about, only Kafka and MapR Streams make the cut for the modern needs. Persistence, performance, and another one, and compatibility, I guess. But they are a different thing from the processing. And I've talked mostly about the transport. Now, there's one that's confusing. It's Kafka Streams. It is not like MapR Streams. It is a processing technology, but it's over there. And those should all work with the key transport technologies. So that's how they all fit together. One last?
Do you have any plan to support Kafka Streams, which is a library, not a full stream processor?
Do we support Kafka Streams? I haven't tested it. It does depend on a few features of the Kafka 10 API. I'm not sure. But it should just work. Almost all applications just work on MapR Streams. There's a few small things that we're going to fix. For instance, the message ID offset increments by 1 in Kafka 0.9. It still implements in MapR Streams by the number of bytes. Some things assume 1 and therefore have troubles. But otherwise, it should just work. The model of concurrency that it uses is very simple, depends entirely on Kafka partitions, and all of those semantics are preserved. So shouldn't be anything special. Flink just worked, and Flink does amazing things. Spark had some issues, but that had to do with native code loading and class loader sort of things. And Kafka Streams has none of that. So it should be very easy. We haven't tried it yet. Well, thank you very much. Our time is up, but I'm happy to talk in the hallway or at the booth, or even at lunch. Anybody want lunch? Obviously, the people who really wanted lunch have already left. They'll be in front of us in line.